Welcome to our discussion on the rules of logarithms. At this point, you've already seen the basics of logarithms, and now we're going to look at some of the rules, the ways that we can use these to solve various problems. First one is the product rule. Now, we're going to be going through the product rule, quotient rule, and the power rule, and rather than thinking of these as brand new rules, let's try and relate them back to something we already know. You'll recall that when you're taking a log of something, this equals a number, right? And the number is basically a to that number equals mn. So if we take this and set it equal to, let's say, y, then we know a to that number y is going to equal m times n, right? So this is really just a power in disguise. So if we take a and raise it to the y and it equals mn, and y equals this thing, then if we take a and raise it to this thing, right, this whole thing which is just a number that's equal to y, isn't that also going to equal mn? Well, if we're going to take the left-hand side of this equation and make it the power of a, we have to do the same thing on the right side. So let's let a be raised to both of these things. So now we have a raised to the stuff in yellow, right? And on the right hand side we have a raised to the stuff in green. But because we're claiming that these two things are equal, then if we take a and raise them to those two things, they'll also be equal. But we know that when we take a and raise it to this yellow thing, which is just equal to y, we're going to get mn. So on the left hand side we just get m, right, times n. On the right hand side, all right, we don't know what these are, but we know this is a number, right? And this is a number. So it's a raised to something plus something. Well, if you remember your rules of exponents, if I have x raised to the 2 plus 3, isn't that x squared times x cubed? Right? We normally do this in reverse. If we have x squared times x cubed, we know we can add the exponents. But we can go backwards, right? If we have this number, we can break it up. So if we have a raised to these two things separated by a plus and minus, isn't that the same thing, right? Isn't this just going to equal a to the log base a of m times a to the log base a of n, right? Just using the simple rules of exponents. And now again, we know that log base a of m equals a number. And if we think of just log base a of m, let's go back to what it means to be calculating log base a of m. We'll say this equals some number, we'll call it p, just so it's a new number, right? We don't know what it is, but we know it's p. But we know that basically this is saying that if we take a and raise it to this number p, we get the answer m. So if we take a and raise it to this log base a of m, don't we just get m? And can you see the same argument is going to be for this one? So this is just going to be m times n, which of course is mn. So you can see how that's why these two things are equal. So that's why this rule works the way it does. That if you're taking the log of a product, it's the same thing as the sum of the two logs, and it comes from the rules of exponents. We know that if we are dealing with the rules of exponents, right, a sum becomes a product. So that's what's going on. Similarly, we can go through the same arguments to show why the quotient works, right? That it gets back to the rules of exponents. Take both sides and raise a to that power. Now over here, this goes back to the rules of exponents, that if we have x to the 5 minus 3, let's say, didn't that happen because we had x to the 5th divided by x cubed, right? That's where that rule of exponents comes from. And so if we have a raised to these two things separated by a minus sign, right, two different numbers, they're just numbers, we just don't know what they are, right, but they're just numbers, then it ends up being a log base a of m, right, divided by a of log base a of n. It's just that thing, right? That power divided by that power. But we know that if we take a and raise it to log base a of something, we just get m, and down here we also just get n, and there's the mn that we get on the other side. And of course, if we take a to the log base a of m over n, again, just going back to our simple thing of what does it mean to take a log base a of something equals a number, and it just means that if we take a and raise it to that number, we get back m over n. So if we take a and raise it to this number, right, then we're just going to get m over n. So we get m over n on the left, m over n on the right, and there's our second identity. Okay, the power rule. Again, it's the exact same idea. A raised to this, a raised to this. On the left-hand side, we know we're just going to get m to the r, right? Because you're getting better at recognizing this, that if you have log base a of some stuff, right, and you take a and raise it to this whole thing, then you're raising it to the answer, right? Log base a of some stuff, you get an answer, you get some number, and that number is, if I take a and raise it to that number, I get m to the r. So if I take a and I raise it to this thing, which is the number, right, just written differently, then it means I get an answer of m to the r. So on the left-hand side, we get m to the r. Simple. On the right-hand side, well, now, what happens if we have x raised to the power of 3 raised to the power of 5? If we raise something to a power, do you remember what we do? What the rule is? The rule is we have 3 times 5. Well, look at here. We have something raised to a product, right? These are both just numbers. So this is a to the log base a of m raised to the r, right? We could do it in either order. We could do a to the r raised to the log base a of m, or we could do a to the log base a of m raised to the r, right? It doesn't matter. We could switch to the place of these, and it's still the same thing, right? X to the 5th cubed, right? It's still the same thing. So I just wrote it in this order because now we can see very plainly that a to the log base a of m is just m. And now we have m raised to the r. So on the right-hand side, we also get m raised to the r. And yes, they're equivalent. Okay, so great. So now you've seen why these rules work. How do they help us? Well, this rule we've just looked at, this is the biggest one. This is the one we use the most. Because now, if we have a variable trapped as an exponent, and we want to solve for that variable. So we've seen examples of this, like our great friend exponential growth and decay, e to the kt, right, where k is some constant, and this equals some amount after some time t, and maybe you're trying to find how long it takes for your stuff to double, or how long it takes until you have X amount of something, right? So you need to solve for time. Well, you can't solve for a variable when it's trapped up here as a power. You need it to be down on the regular baseline, right, with our normal numbers that we can solve as we're used to solving just regular algebra stuff. Well, now with this trick, you know that if I take a log, right, of something to a power, the power comes down in front. So I can take log of both sides, right? I'd get rid of the a to 0 first and have e all by itself. So now I have a over a naught, right? A sub 0 equals e to the kt. And now I can come along and I can take a log of both sides. And if I take just a regular log of both sides, any base I want, well, this is just a number, so log of it's just going to be a number. And now I know that from this rule, this is going to give me kt times log of e. Again, a number, I can take a log of it, and then I can solve for t, right? I can divide both sides by log of e, I can divide both sides by k, and now I can solve for t. But why would I take a log when instead I could take a natural log? Because if I'm going to have this log of e left here, why not do natural log instead, right? It's just a log base e instead of log base 10 or log base 3 or some other base. This is still a number. This is still a natural log of a number. Still just going to give me a number. But now when I do this, natural log of e just equals 1, right? They undo each other. So it makes the math a little easier. So now all I have to do is divide both sides by k, and I finally can solve for t. So this rule is going to come in handy a lot when we're dealing with these types of things. Let's look at some other examples. If we're given that log base 5 of z equals 3 and log base 5 of y equals 2, we can now evaluate any of these combinations of things by just using the rules and splitting them up. The first one, very simply, right, we're taking a log of a product, so it becomes a sum of those two logs. And now we know that log base 5 of y is 2, log base 5 of z is 3, so we get 2 plus 3, and the answer is just 5. Simple. Okay. Next one, again, we have a product, so we can break up the products, and then we can rewrite 125 as 5 cubed. And so now log base 5 of 5 to a power, we just get the power. All right. Technically, if you wanted to, this is using the power rule, where you just get 3 times log base 5 of 5, right? Because we have that rule that if we're taking a log of something to a power, the power comes down in front. And then log base 5 of 5 just equals 1, and you get 3 times 1, right? Same thing. Here, power comes down in front. Then we have log base 5 of y, which we know is 2. Substitute everything in, and there we go. You can walk yourself through the next one and the next one, right? It's just a combination of everything. First things first, take the product, write it as a sum of two logs. Now tackle each log individually. The power, right, rule brings the 1 over 30 in front. Then we're just left with log base 5 of z. Again, power comes down in front. Left with this. Substitute in what we know those two things are equal to, and do the math, and you're done. It's that simple. Now, what about if we want to kind of write something that's more algebraic out in expanded form? You might ask, why would I bother with this? There are applications where this is helpful. Usually when you're going to take derivatives and things like that, it's easier if you can kind of break them up and then take derivatives of each piece rather than having to worry about products and quotients and things like that. So you can take something as ugly as this and then break it up into all its pieces. The top piece divided by the bottom piece means log of the top piece minus log of the bottom piece. Now this piece is also a product, so we can turn that into a sum, right? And now each piece is kind of broken down into its smallest little factors, and now you can deal with the powers. 2 comes down, 3 comes down, 4 comes down, and we're done. Please don't think that you can split this up. A lot of students go, oh, well, hey, look, it's a difference. That becomes a quotient. No, it's the other way, right? You have to take a log of a quotient becomes difference of logs. Log of a difference does not become like a quotient of logs, right? It doesn't work in reverse. You got to remind yourself of what that rule is. The rule is if you have log of a quotient, right, a fraction, then you can have a difference of those two logs. But log of a minus b, which is what this thing is, right? Something minus something, does not equal log of a over log of b, right? It doesn't go in reverse. These things don't work in two directions. Similarly, we can work with this one, rewrite it as a power, take the power out in front. Now we have a product. Take that product, split it up into 3 pieces, right? Then take each of those powers, bring those powers out in front of each log, and then you can just distribute that one big power that's in front onto each individual piece to get rid of your parentheses. And now you just have 3 different logs. And again, you're probably thinking, well, why is 3 logs better than 1? Well, if you're trying to take derivatives and deal with things, it's much easier to deal with a simple log, right? Just log of c or log of y, than to try and deal with a log of something to a power. You can also work in reverse. You can start with something that's all expanded out and combine it. The first one, right, we see that subtraction, difference of logs. We know that it's now going to be a log of a product. With the second one, we take all of those constants that are in front of the logs and realize that they become powers, right? And then we now have a sum of two logs, which becomes a product. So you can see we're doing the same rules, just in reverse. You deal with the powers first, then you deal with products and differences, right? This one, bring the power up, so now it's 5 squared. Then you've got log of 9, minus, so now it's all just powers, right? There's nothing in front of them. So now you can combine the plus as multiplication, 5 squared, which is 25, 25 times 9. And then you can now deal with the subtraction, which is division. So you've got 25 times 9 over 75, and that whole thing simplifies down to just log base 2 of 3. Last example. Again, we're going to deal with that stuff on the inside, right? It's deal with the things inside the parentheses first, and we combine up all of that. Take the sum and make that a product. Take the difference, make that division. Now we finally have just natural log of one thing. Now we can deal with the power out in front and turn that into raising it to the 1/3 power, which is really just written as a cube root. Okay, common logs and dealing with digits. A positive number k has n plus 1 digits if and only if log of k is in the interval n to n plus 1. It's just an interesting pattern that mathematicians have discovered that allows us to kind of deal with certain things. Don't worry about it. Doesn't come up too much, but just so you know that if you have a positive number k, it has n plus 1 digits, meaning the number 253, right? That's a positive number. This has 3 digits. So in this case, n equals 2, right? Because it has 2 plus 1, 3 digits. That is true if and only if log of 253 is in this interval. So that just means that log of 253 is going to be less than, well, n plus 1, so we're up to 3 number of digits, and less than or equal to n, which is 2. So log, right, log base 10 of 253 is somewhere between 2 and 3. Well, what is log base 10? Log base 10 of 253 equals some number y means that 10 to the power of y equals this number. Well, 10 to any power is just 1 with a bunch of zeros, right? So in order for 10 to be raised to a power to equal this, well, 10 squared is 100, 10 cubed is 1,000. And we can see that 253 is in between 100 and 1,000. So it works, right? So it's basically just realizing that digits correspond to powers of 10. Because in the number 253, 3 is the ones digit, and 1 is 10 raised to 0, right? 5 is really equal to 50. That's the tens digit. That's 10 raised to the 1. And 2 is really equal to 200, right? This is 200 and then 50 and then 3 more, right? So 200 is 10 squared is 100, right? So it's 2 of those. So that's why we know that if it has 3 digits, it's at least y squared, because the smallest 3-digit number would be 100. So that's why we can have this equal to, right? Less than or equal to 10 squared, because 10 squared would be 100. And the biggest 3-digit number we could have is 999, which is just a little bit less than 1,000, which ends up being 10 cubed, right? So that's why we know log of it is always going to be less than 3, because if it was 3, it would be at least 1,000, right? And it would have 4 digits now. So that's all this is doing, is it's relating digits back to powers of 10. All right, how about estimating a large number? We can estimate super large numbers kind of with this idea of the digits right? We know that e to the 700 is a super huge number. We know it's k. We can take the log of both sides and get log of k equals log of e to the 700, which is 700 times log e. Log e is just a number. You can write it times 700, and then you get 304 point blah, 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 blah. Right? You get a number. So now we know that log of k equals 304. Since log of k is between 304 and 305, we know that the number k requires 305 digits to the left of the decimal point because it goes back to this log formula. Right? Log k is always in between n and n plus 1, where that's the number of digits. So since log k is in between 304 and 305, we know that the actual number is going to have between 305, right, and 306 digits. Log base k is less than, right, n plus 1 and greater than or equal to n. But remember, the number of digits, right, the number of digits for this number k is n plus 1. So if log k is between 305 and 304, right, from here, it's in between 304 and 305, then that means n equals 304, which means the number of digits, right, of k is 305, n plus 1. So that's why we know that k is going to be at least 305 digits to the left, right, of this number. So 10 to that, right, really, really big, and there's our estimation for that number. Okay, so it's a way of basically kind of figuring out a rough estimate of super huge numbers. Because if you tried to put e to the 700 into a calculator, it would just tell you, nope, sorry, can't do it. Change of base, really important. You're going to use change of base all the time. If you have log base b of x, you can change that to log base a of x as long as you divide it by log base a of b. You could also change it to log of x over log of b, because those are both base 10, or you could do natural log of x over natural log of b. So hopefully you can see the pattern. You can change one base to any other base you want. It's just the new base of the original number, x, divided by the new base of the original base, in this case b. You'll normally use natural log and log. And the reason why you'll normally use one of these two is because those are the only two that you have in your calculator. So if you're trying to figure out what log base 3 of, let's say, 20 equals, you can't do that in your calculator. You don't have a log base 3 button. But you do have a natural log button. So you could very easily do natural log of 20 over natural log of 3 and do that in your calculator. Or, since you have a log button, you could do log of 20 over log of 3. And those will both give you the exact same number. Here's another example, right? Go into log or natural log, and you can check that in your calculator and see that you get the same numbers. Okay, how about applying logarithms to growth and decay? As I said in the beginning, that's one of the biggest applications of these rules. We want to remind ourselves what it means for the half-life of any thing, quantity. Right? The half-life of something is the time that it takes for that quantity to go to half of its value. So when they talk about radioactive decay and radioactive half-life, it's the amount of time it takes for the number of radioactive isotopes to be half as many. Yeah, right? You start with 1,000,000. How long does it take to only have 500,000? Right? You start with 1,000. How long does it take to only have 500? You get the idea. The half-life of a substance that is using or undergoing exponential decay at some rate k, where k always has to be greater than 0, can be given very simply as this formula. H is going to equal, H being your half-life, negative natural log of 2 over k. If you want to memorize it, that's fine. You don't need to. You can always just solve it from the original exponential growth and exponential decay formulas, like this example. So in an experiment, 18 grams of radioactive element sodium-24 decayed to 6 grams in 24 hours. We want to find its half-life to the nearest hour. So we're going to use our typical exponential growth and decay formula, right? This is exponential growth or decay. If it's growth, K is positive. If it's decay, K is negative. It's that simple. Plug in what we know. We know that we start with 18 grams, so that's our A sub 0, right? That's our starting amount. So if we start with 18 grams in 24 hours, so we're now going to let T be in hours, right? Because they want us to find it in the nearest hour. So we put in 24 for T. We know that we're left with 6. Divide both sides by 18, so we get 1/3 e to the 24k, right? In order to solve for this, like I said at the beginning of the lesson, we can take natural logs of both sides. Natural log of e to the 24k just gets us 24k. And then natural log of 1/3 is just negative natural log of 3. You don't need to do that. Just plug in natural log of 1/3 into your calculator, right? Because the next step is to divide both sides by 24. And that's where they get this. See, they're just trying to point out to you that this is the formula. If you don't remember what the formula was on the previous page, it was that h equals natural log of 2, negative natural log of 2 over k. Can you see the similarities between these two? Right? The reason why this is natural log of 3 is because we weren't looking for a doubling time. We were looking for a 1/3 time, right? Or how long it went down by 3 instead of going down by 2. In any case, you can solve for k very easily. You can plug this back into your formula, either written like this, or if you left this as a 1/3, right, it just would have been natural log of 1/3 divided by 24, and then that could have been your k. And now you have the formula written in perfect form. It's better to do it this way than to put natural log of 1/3 over 24 in your calculator and get a decimal and then write the decimal into your equation, because now you've rounded, right? The decimal is going to go on forever. It's going to be irrational. So you're going to have to round, you're going to have to truncate at some point, and then now you're getting an estimation. And when you plug that in, now your other results are going to be estimates, and then your rounding error can get compounded, and then you could end up getting the wrong answer on a test or something like that. So you're better off being able to work with this algebraically and just leave it written in this case. Now they say to use that formula, you go back and do all of this. That's fine. You can also not have to deal with this formula. So let me write what we had from the previous slide. We knew that our time, right, our function was equal to 18e to the natural log of 1/3 over 24, remember that was our k, right, times t. If we're trying to find the half-life, if we start with 18, aren't we really just trying to figure out how much time it takes until we only have 9 things left? So just plug in 9 equals 18e to the natural log of 1/3, right, over 24 times t. Divide both sides by 18, and now you get e equals 1/2. Right? Duh, you're trying to figure out what time this e stuff will equal 1/2, so that it'll be your original amount times 1/2. So that makes sense. Okay, now take natural log of both sides. Natural log of 1/2 equals, when I take natural log of e to some stuff, I just get that stuff. Natural log of 1/3 times t over 24. Now divide both sides by this. Well, if you divide, that means you're multiplying by its reciprocal. Okay, if that's making your head swim, then just take it in steps. To get rid of this fraction, multiply both sides by 24. Right? Multiply by 24, those cancel. Now, divide both sides by natural log of 1/3. Right? And there's t. T equals this. So if you do 24 natural log of 1/2 divided by natural log of 1/3, you'll get this exact same answer. How is it that it's natural log of 2 over natural log of 3? Well, because if we wanted to change this to natural log of 2, it just would have become negative natural log of 2. Because remember, this is 2 to the negative 1 power, and that negative 1 power comes down in front. Same thing here. This would have been negative natural log of 3, because this is 3 to the negative 1 power, and those negatives cancel, and that's why those two things are exactly the same. If you plug that in your calculator, you'll see you'll get roughly 15 hours. So if you want to memorize that formula, that's fine. It can save you a little bit of time, but I'm not a big fan of memorizing more formulas, especially if I don't need them, especially if all I have to do is work with the standard exponential growth and decay formula and then just work through it logically, right? If I'm looking for half time, then I set my a of t to be half of my starting point. And if I'm looking for doubling time, I just set it to be twice that. So now I've got a more general way of solving all of them. Radioactive carbon dating is a simple or a common example of kind of this half-life idea. So we can see that this carbon-14 decays radioactively with a half-life of 5,700 years. After any organism dies that contains this carbon-14, and just about everything does contain it, the age of its remains can be calculated by determining how much of the carbon-14 has decayed. So in 1960, a group of specialists from the British Museum investigated whether a piece of art containing organic material found in King Tut's tomb had been made during his reign or whether it belonged to an earlier period. We know that Tut died in 1346 BC according to records and ruled Egypt for 10 years. What percent of the amount of carbon-14 originally contained in the object should be present in 1960 if the object was made during Tut's reign? Well, the half-life of carbon-14 is approximately 5,700 years, so that means 1/2 of the original amount equals the original amount times e to the 5,700k, because 5,700 would be our t, right, our time. Divide both sides by a sub 0, right, the original amount, and then you get 1/2 equals e to the 5,700k. Take natural log of both sides, you get natural log of a half equals 5,700k, divide that by 5,700, and you get k equals that negative 0.0001216 decimal. You can do it yourself to verify that's what you get. If we sub that back into our original formula for exponential growth and decay, we now have the general formula for carbon-14. Okay, so now we can let x represent the percent of the original amount of carbon-14 in an object that remains after t years. So x times the original amount is going to be the original amount times e, so x just represents the e part. The time t that elapsed between King Tut's death and 1960 was 3,306 years. So the percent x sub 1 of the original amount of carbon-14 remaining after 3,306 years is just going to be this formula where t is 3,306 years. We put it in, and there should be roughly 66.897, right? Almost 67% of the original amount should be left. Well, King Tut ruled for 10 years. So the time t1 that elapsed from the beginning of his reign to 1960 is 3,306 plus 10, or 3,316. And if we rerun everything with 3,316, we get 66.816. So thus, if this piece of art was made during their reign, the amount of carbon remaining in 1960 in this piece of art should be somewhere between 66.816 and 66.897%. Now all you have to do is go and measure how much of the carbon-14 is in that art piece. And if it's in that range, then you know it was made in that time. If it's different, then you know it wasn't. And in fact, you can use the formula to solve backwards and figure out in what year it was actually produced. That's how they can date something. Based on how much carbon is remaining, you can solve backwards in this formula for t, and then figure out how old the object is. Okay, that's going to be one of the most common uses for the rules of logarithms. So please make sure that you understand how to use the basic formula, right? It's all about working with this basic formula. You have to be able to solve for k and then work with this formula to then solve for t given some situation. And that's all you need to know.